All right, well, let's start. So today, the planned part of this session was to talk about some of the thinking that to change some of the default settings of the HDF5 library in 2.0 release. And I say thinking because obviously it may be modified based on the feedback. And after that, I was going to briefly talk about some of the benchmark results that I recently analyzed of some cloud optimized, but also analysis ready HDF5 files. So I think that's usually I talk about HDF5 files that someone else created, and I had very little input. This time I was not the one who created those files, but I had more input how those files were created. And so that's, I think, is an interesting element. So first, I will talk about these changes, well, thinking to change some of the default settings in the library. And I don't know how many people follow the HDF library releases, but the next one very likely will be the famous 2.0 release. And there is a number of changes that are currently being planned for that release. This wiki page on the HDF5 GitHub repository currently serves as the sort of holding place for many ideas. Depends what kind of user you are. For example, you may care about that from 2.0, the version numbers are actually going to follow this semantic versioning convention. Previously, people got confused that 1 point something, that the major number never changed and basically meant nothing really as far as the releases go. Well, now the intention is that semantic versioning convention is fully followed. The other thing also, I think, for some kind of people maybe let me see. Okay, well, not really written here, but we'll be dropping of auto tools for building the library. So from 2.0, current thinking is only CMake build system will be supported and available. And along other things, there is this thinking about updating the library defaults. And right now, there are 3 defaults, but the third one is somewhere else, and I'll mention why. So the one that so this issue on GitHub is number 5272. This is the HDF5 GitHub repository is using the fairly new feature that now you can have parent issues with sub issues. And only earlier today, I learned that you can have up to 500 sub issues and up to 7 levels of hierarchy in sub issues. So you can have sub issues with sub issues that have sub issues all the way from here. So, someone at GitHub is adopting the HDF5 way of thinking. And so one of these is to increase the default dataset chunk cache, which was set since the beginning of HDF5 library to 1 MB to something bigger. And the suggested new size is 8 MB by default. The main thinking is, again, towards the users who are not technically skilled or interested to learn about HDF5 or use software where HDF5 is sort of the 5th level of software stack, and they cannot really reach the library to change many of its settings through all the the software layers there. And so those kind of things to make a library in some ways more modern, if you will, in some ways. And so this is one. The other issue that's fairly new is to I think change the way how HDF5 files are created by default. And so instead of basically going back to the earliest possible library version when files are created, and by that forcing some of the structures in the file to use the older structures that are apparently slower or yield some other issues later on in performance. That the library now basically creates file that has a more modern more up to date, well, more recent library version. I'm trying to think about how to frame it, but you know what I mean. What that means is that perhaps some of the older library versions will not be able anymore to use those files, because if this lower library version of the created file is recent than the library version that people are using to read that file, there could be some issues. And so that's one of the downsides of these things. But again, nothing is set in stone. Obviously, we're thinking how to announce it more effectively to the community for feedback, but those two things are currently listed under this parent issue. If people want to leave a comment, I think the best way would be to go to these GitHub issues and leave comment there. But as I said, I think we'll have to find a way how to announce it on HDF Forum, for example. The third one that goes along this kind of default values, but it only affects if you use the read-only S3 driver, is the page buffer cache type. And that page buffer is absolutely essential if anyone is going after HDF5 files in the cloud. And so right now, again, by the library default, this page buffer is always 0. And so you have to actually set it to some non-zero value. And we would like to change that, but only if people also use a read-only S3 driver. And so those are the things. It's not listed here because it's under another big parent issue, which is cloud optimized HDF5. And I think that, there you go. This is this issue actually for this one. So, and the reason why I didn't qualify for the other parent issue where library defaults is only because it would apply to raw3 driver. So that's about this library default situation. Any questions?
Not a question per se, and I'll add some comments on the GitHub issues as well. But what do you think about adding environment variables for all of these so that in the use cases you suggested, somebody else could set the environment correctly for the naive users? Or if it's 5 levels deep, then you could, update that at runtime and didn't need to figure out how to update all the stack.
I haven't heard about the environment variables. I heard thinking about a configuration file.
Yeah, well, there's lots of ways to do it.
Yeah,
but,
yeah. I think that configuration file would be an interesting option, so that I could then send to someone that configuration file and say, here it is. Use it, for example. But yeah, environment variables, perhaps that's another option. I'm personally not excluding all the other approaches. I'm just trying to figure out how to help. As I say, I kind of interact mostly with users for whom HDF5 is sort of, I get data from HDF5 files, but I just care about data, not about, is it this format or that format. And so they sometimes have issues with performance that it goes beyond their technical level to really troubleshoot or figure out what goes on. And I would like to avoid the kind of the conclusions they usually come up with, that HDF5 is the problem and it's difficult to work with.
Mm-hmm.
That's basically
Oh,
where this
absolutely.
comes from.
Right. Sure. Yeah, I'm just trying to find some easier ways into that, rather than in addition to the possible, which I think is a good idea, to update the defaults for the builds. But even so, there might be cases where we want to add a bunch of environment variables for things that we don't update during the 2.0 refresh.
I agree in general.
Okay.
I agree on the environment variables. They're easier to do on a run-by-run basis, whereas config files, it's kind of depending where they are, it can affect multiple jobs at a single time versus, with an environment variable, I can set it in my submit script and go, and I know it's just going to apply to that job.
Yeah, absolutely.
All right. If there are no more questions about those kind of things, we can move to the other part of my session. So, so these benchmarks of these HDF5 files. So this comes from a project that I'm involved with, where we are trying to, and it's called Open and Fair Fusion Plasma for ML, for machine learning, and it's a project with several universities, MIT, William and Mary, Auburn University, University of Wisconsin, as well, where we're trying to increase the sort of the open science, the capability of fusion plasma data, and all towards improving ultimately the machine learning applications that are being built on top of that data. And so in this case, these files are also, I call them analysis ready, because typically the data that goes into files when it comes to these fusion plasma devices is per one experiment. And if you hear me say shot, in fusion plasma world, a shot is one experiment at trying to light up plasma into a fusion plasma device. And so the data that is collected while they try to start the plasma and what happens afterwards are called signals. And there are all kinds of signals, whatever the instruments are mounted on this fusion plasma device and whatever they measure. Each observation is called a signal. And so one shot, which is one experiment, can have many signals associated with it. And typically, traditionally, because it was one specific event, you try something, there is some history that the plasma developed or not, or develops and then collapses too soon, whatever happens. That's one single event. And so the analysis of the data was, and the storage was one shot per file. And however, in this case, we tried to put more than one shot. In this case, there were 500 shots in the single HDF5 file, and also the way how the data was laid out in the file was done with specific care, in order it wasn't done to be fast at writing. It was done in a way to make it fast to analyze the data. In other words, to read the data from those files. And so that's why I went ahead and called those files analysis ready files, because that's where you kind of put more thinking and concern about many times the data will be read from the file, as opposed to be very efficient when the writing file one. And also these files happen to be cloud optimized as well, because we wanted to compare the performance when the files will be accessed in a local file system or when they would be in S3. And also what was new regarding these files or the access to them, I used Dask. And I don't know how people familiar or not, but Dask is a very popular Python framework for distributed computing. And there are many ways how Dask can be employed. And as you can see here, I'm hovering around them. I use Dask futures. And Dask futures are basically the same thing as what you get in Python with its concurrent futures package. The only reason why I wanted to use Dask is because if we decided, and if we still decide, we have not decided yet, if we actually wanted to use a Dask cluster in the cloud, then it will be very, very easy to transition and use the same code for that kind of setup. Whereas if I used concurrent futures in my benchmark code, then I would have to make more changes because concurrent futures cannot work with a Dask cluster or any other kind of cluster for computing cluster. And that was the only reason. But other than that, as it was used now, the Dask futures are very similar to the Python's concurrent futures. So I'm not going to go through all these things. We have limited time, but how were these files different between each other? Well, one file, when it was created, we followed this shot-centric approach. So we created the HDF5 groups for the shot and the signals, and then we wrote out all the signals per shot, and then moved to another shot, the same thing, and then to another shot, and the same thing. The other file used a different approach, although we did create all the HDF5 structures the same, the groups. What was written out were actually all the same signal, but from all the 500 shots. They went first. And then some other signal, again, from all 500 shots was written out afterwards. And then the third signal from all 500 shots were written out, and so on and so on. And I developed some Python script there where I could, because this file was cloud optimized, which means that we used paged aggregated file. I developed a Python script where I could actually see which HDF5 datasets were stored in which file page. And so I could compare the first and the second approach and see if there were any difference how the datasets were laid out. And there were some differences. Although I have to say, we learned that HDF5 library has a mind of its own. So you don't really get to control that much when the library writes out things to the file, but there were some difference. And we said, okay, it's good enough for what we're trying to do at least. And so those files were put both in a local file system, EBS, attached to an EC2 instance, and also put in S3 at Amazon. And I used an M5 4x large EC2 instance, which has 16 virtual CPUs, which I found somewhere. I think that it's effectively 8 physical cores, and also that instance had 64 gigabyte memory. And long story short, I ran those benchmarks. There were some results. I analyzed them, and I guess I'll go over the most important benchmarks. And if there are some questions later, we may, see if we can answer them with some other plots. So here is the performance when the files were local. On the x-axis, you see the number of Dask workers, and I tried with 1, with 2, with 4, with 8, and with 16. So wherever you see this little kind of a solid circle, that's where we actually had the data. And because it was local file system, I used several combinations how I ran those benchmarks. So in other words, I used page buffer or not. And when I used page buffer, I used either 64 megabytes or 264 megabytes per Dask worker of page buffer. I also used a specific file, and then I tried to read the data in 2 different ways. So I was going after shots, rather reading all the signals for one shot, and then going to another shot, and then going to another shot. or I was going per signals. In other words, I was going one signal for all the shots and then read that way. And I was applying this different access order to either the shot laid out file or the signal laid out file. I'm trying to mix up things and see how everything goes. And so that's why you have so many so many results and so many lines with different colors. So here on the left, you see basically page buffer, what kind of data access order was, signal or shot based, and then what kind of file was used. Was it shot layout or signal layout file? And if you can maybe notice, there's this thin pink line. That's the line of linear performance for the increasing number of Dask workers, and also it's a performance ratio which I'm plotting. And performance ratio is also not the seconds, not the time, because I thought that okay, but you have a computer that's faster and the other one that's not. So I tried to normalize them, and the way how I normalize them is I chose what I call the lazy scientist benchmark. And the lazy scientist benchmark meant that there was a person who doesn't care about all these settings of the library, doesn't care about all these Dask thing. He just wants to read the data from the file, which meant that there's only one worker, no page buffer, and just using reading by shot, because that's how usually fusion plasma physicists are doing it. They're reading data by shot. So that was the lazy scientist benchmark. And so all these numbers that I'm plotting here are actually normalized to that particular benchmark. And as you can see, there is the best improvement that I got with 16 Dask workers, again, running on this single EC2 instance as separate processes, because the HDF5 library is not multi-threaded yet. Gave about just under 10%, 10-time improvement. So in other words, from the lazy case to the best case, it was 10 times improvement to read all the data from the file, from all 500 shots. And there's interesting clustering that now you have this group of a lot of cases that really didn't excite by the performance. And then there are two of them which are kind of standing out. And the ones that are really, really good are the ones that really didn't use page buffer at all, which kind of is a thing for a local file system, that they're so fast compared to cloud object storage that you really don't need this page buffer cache help. The next one, the second group of these things, are actually when the page buffer cache was used. But if you can see here, the file was shot layout, and the way how the data access order was per shot. And every other combination of these things really didn't excite, as I say, when the files were locally. When those files were in S3, there were a lot of changes. So for one, I never tried to use case benchmarks with no page buffer, because that would take forever, and I mean it, forever. And so that was not an option anymore. So in this case, the lazy benchmark was actually using page buffer cache of 264 megabytes. In other words, the largest one in this of all the benchmarks, but still one worker. And the result here, first of all, they follow the linear increase very well. So like these cases are essentially linear within number of Dask workers, which is interesting. I didn't get that linearity when the files were in the local file system in the EBS attached to EC2, but here when they were using EC2, when the files were in S3, there was literally, even in some cases, performance was even more than linear increase. But eventually, for the 16, came close. So I didn't try more. I analyzed the data. after I destroyed the EC2 instance. So I was lazy to set it up again, but I should have tried maybe with more Dask workers just to see when things would stop falling, being linearly increasing, but I haven't. So maybe there was some number of desk workers further that could have still had fairly decent linear increase. And as you can see, the best cases are with the largest page buffer cache of 264 megabytes, and when reading by shots, and when the file had shot layout. And this is the thing that I noticed throughout all these results, that the signal file and reading by signals somehow was not as successful as I expected compared to the shot layout file and reading by shot. And that can be that we kind of missed something to really lay out the data in the file the best way, or that just something else was messing up. I haven't really done that deep analysis to know exactly why, but there was really significant change in the performance. The shot layout file, reading by shots, was always consistently best. Then there was coming the signal layout file, reading by signals, and all those mixed cases where you could like reading by shots, but the file was signal layout, or you're reading by signals, or the file was shot layout. Then really didn't have good results at all. And finally, for the end, this is like all the runtimes in seconds, just to show sort of the scale of different benchmark results. So as you can see, the worst kind goes, for example, all the way to 2,500 seconds when the file is in S3, for example, to read. And then the best you can get all the way down to sort of 6 seconds, almost 7 seconds when the file was local, and for the largest number of desk workers. So yeah, it was quite a range of performances. And there were some interesting cases where you can see these benchmarks kind of follow this usual line that the performance is increasing with the number of Dask workers, and then suddenly they decide to become worse with more and more Dask workers. So the jump ship in terms of, they go from this cluster of results back to this cluster of results. Sorry, I was zooming in while I was looking at here.
So do you understand why that happens?
I have to see which the cases are. I have not looked at. No.
Yeah.
I mean, frankly, maybe if I repeated enough times the benchmarks, maybe that would go away or something. But there were some changes that, this is a local file. So there was some degradation in local when the files were local with some number of Dask workers. And I don't know if that was some transient issue with this instance or whatnot. But I repeated a couple of times these benchmarks, and they all came not with the same degradation, but kind of looked again, the same type of degradation was happening. And I kind of must be something with EC2 instance or something, but I haven't followed up. So anyway, these are the actual seconds for this column, total runtime, how much it took to read all the data from the file. And again, as I say, not surprisingly, the local files dominate top 8 results. But the S3, the best S3 result, when you look at it in absolute terms, in other words, in actual seconds, not really bad. I mean, 16 versus 7 seconds, that's not bad. I mean, it's still within, I'm going to grab a cup of coffee and it'll be done kind of situation. And also here, it's always for the larger number of workers. So again, S3 with 16 is almost all the other cases with 16 or 8. So like I said, it wasn't bad at all. I actually thought this was pretty good overall performance for files in S3. And that's where I would stop. The other things are more, kind of looking at various things, but nothing really changes the overall conclusions. So if there are any questions, I think what I was interested in mostly is to see whether or not Dask can help when reading the data, and if the file is cloud optimized, and you go after it in S3, can you have a comparable performance with something that file would be in a local file system? And in this particular case, it seemed to be, not really the same speed, but again, 16 seconds versus 7, it's kind of like, okay, it's doable for the people that are going to use this data, those kind of things. So that's all, really. Unless more questions for anything we talked about, we can wrap this up.
I wasn't quite clear on how performance ratio was defined. It seems I would have expected it to sort of start at 1 and go from there and not be close to 0. That suggests that like the numerator is 0 in your ratio.
No, what I did is it's not really 0, it's close to it. Like here it's
Right.
0.3. So, but that only means that there was a case that was slower than my lazy benchmark that I used as the normalizing factor. And that's all. For example, here, this particular case, and I have to zoom in more just to be able to show. So my lazy case was no page buffer, reading by shots, the file is shot layout, and the number of workers is only 1.
And the performance ratio is a ratio of time?
Yes. Their times, and I just normalize their times to this one, to this case. Because, for example, on my laptop, I had better results than on that EC2 instance for local files. And I said, well, in that case, throwing seconds around is okay, but still doesn't tell anything because some faster computer might have better seconds. So let me trying to sort of make these conclusions maybe a little bit less sensitive to a particular computer that was collected. So that's why I tried to normalize them. So in this case, it was used, and then the worst case was using you see page buffer of 64 megabytes, reading by shots, but the file was signal layout, and again I had number of workers 1, so that one was the worst by far. And this is for local file. So that's why some of them went under 1. Okay, any more questions? If not, thank you for joining, and see you next month personally, but someone else from the company will be next week. Oh, there's a chat, something? Oh, thanks. Okay. No, thank you. Appreciate it.
Yep, it'll be Scott
ahead.
next week. All right. Thank you, everyone.
All right. Thanks.
Bye.
Bye-bye.
Thank you.